Good day, students. This lecture will be focusing on the continuation with our discussion on Chapter 2, which is measurements. I am encouraging you to prepare pen, paper, and scientific calculator while you are watching this recorded video. But before that, let me remind you first on the following reminders on our upcoming laboratory on Wednesday, July 30, 2025. You can take a screenshot of this slide and share it with your classmates or group members, and reminding everyone to prepare the necessary materials for the upcoming laboratory experiment, except for those that are already available in our laboratory, like the glasswares, beaker, graduated cylinder, watch glass. You don't have to bring all of that. Only those that are not available in our laboratory. All right? See you on Wednesday with our laboratory experiment. So with that, let's proceed with our discussion on lesson 2.3, significant figures. Previously, we have discussed scientific notations and accuracy and precision. I hope you still remember that. And this one for significant figures, this might be also a familiar topic with you, but I have a question here that I'd like you to answer quietly. So why do you think the usage of significant figure is important? And the answer is because it helps us to reflect the accuracy of the measurements that we use. And why is that so? Because in every measurement, we have this certain digit that we are uncertain. So we must use numbers that are meaningful. We can never be 100% accurate in terms of getting a measurement. For example, how many significant figures or SF do you think 3.274 have? The answer is 4. All of them are significant, but the numbers 3, 2, and 7 are the numbers with high accuracy, and the last digit is an approximation. So that's what I mean by having uncertain numbers in a certain measurements. Now, in significant figures, we have this 5 major rules that you have to remember. Literally, this statement means literally what the statement means. So all you have to do is to remember the words, the rules, the 5 rules, so you can apply it in identifying the numbers of significant figures. All right? So for the first one, all non-zero digits are always significant. Just like what we have saw on the previous slide, the numbers 3 something na, all of those are non-zero. So all of them are significant. So ibig sabihin, in this number, in our example, 791.22 meters. So this measurement, how many significant figures do we have here? If your answer is 5, you are correct. Now, next, that's just it, no? So whatever the rules says, the statement is, just memorize it. Next one, rule number 2 is all zeros before the first non-zero digits are not significant. Meaning, in this example, in this measurement of mass, 0.0009 grams. How many significant figures do we have? If your answer is 1, you are correct. So remember that all zeros before the first non-zero digit is always not significant. They are not counted as a significant figure. All right? Next, all zeros between significant digits are always significant. Now, in a case wherein we have zeros in between, it looks like the sandwich to zero, we can consider them as significant. For example, in the measurement 0.005005 meters, how many significant figures do we have? If your answer is 4, then you are correct. Following rule number 2 and rule number 3, for rule number 2, all zeros before the first non-zero digit are not significant. But if the zeros are in between a non-zero digit, then all of them are significant. You got that? All right. Next, for rule number 4, we have zeros to the right of a non-zero digit and to the right of the decimal are always significant. For example, we have 360.00. So the zeros after the non-zero, so we have here the first digit, non-zero digit, all of this can be considered as significant. So if your answer here is 5, then you are correct. So meaning, if we have a decimal place right after a zero, then we can consider that a significant figure. And lastly, for the last rule, zeros at the rightmost end of the measurement that lie to the left of the understood decimal point are not significant. For example, 80,000. Where is the understood decimal point in this measurement? It's always on the right side of the last digit. But since all of this are zeros, we cannot consider them as significant because this is only a understood decimal point. But if it is clearly shown that it has a decimal place like this, all of them could be significant. But if this is the case, on our example, let me just delete this. Yan. So we only have one significant figure here. So if you want this to be all of 5 significant or more, you have to put a decimal, clearly seen decimal place on the numbers. I hope that is clear because those are the 5 rules of the significant digits that you have to remember. Now, I would like you to apply the rules by identifying how many significant figures do the following measurements have. I'd like you to pause and think of your answer. Then you can check your answer on the uploaded file on our Canvas LMS. Next, now, what if we proceed with doing calculations in significant figures, just like what we did in scientific notation? We have this only 2 rules in addition and subtraction, as well as multiplication and division. You just have to do the um, needed addition, subtraction, multiplication, and division. All you have to do is to finalize your answers by following the rules. So if you are adding and subtracting decimal places or significant figures, you have to make your final answer with the fewest decimal place. And if you are multiplying or dividing decimal places, significant figures, you have to follow the fewest or least significant figures. So let's apply this on a certain examples. Let's have first the addition and subtraction on the left side. So you can freely use your calculators here, but remember that it's not always the whole numbers that you can see on your calculator that you will have to write on your final answer. You have to decide based from the rule. For example, if you will be putting 10.11 minus 3.6, or you can just do it mentally. On your calculator, we will have an answer to what? If your answer is 6.51, that's correct on your calculator. But following the rules on the significant figures, we have to follow the fewest decimal place between 10.11 and 3.6, which has a fewest or least decimal place. The one with the least number after the decimal place. So we have here 2 decimal places for 10.11 and then 1 for 3.6. So our final answer should be 6.5 only, not 6.51 on your calculator. You get that? So if you are following the rules in doing this on your significant figures, we have to follow the fewest decimal place for addition and subtraction. Now, on the other hand, the second one, 89.332 plus 1.1, on your calculator, it will show 90.432. But we only have the least decimal place, which is 1.1. So your answer here should be only 90.4. So following the rule that you have to follow the least decimal place. Now, on the other hand, if we are multiplying decimal places on and dividing it, we have to follow the fewest significant figure. If you will be putting 190.6 multiplied by 2.3 on your calculator, you will get 438.38. But we have to follow the least or the fewest significant figure on our given. So in 190.6, how many significant figures do we have? We have 4. In 2.3, how many significant figures do we have? We have 2. So how should we write our final answer? We have to get at least 2 significant figures on our final answer. So our answer should be 430. Following the rule number 5, that the zeros before the understood decimal place are not significant. So this 0 is not significant. We only have 2, 4, and 3. Last, we have 6.85 divided by 112.04, and you will get a bit long amount on your calculator, somehow 0.606113888 something, right? Now, knowing that we have to follow the least significant figure, for 6.85, we have 3 significant figure. And for 112.4, we have 5 SF. So we only need to follow 3 significant figure. So our final answer here should be 0.0611. Following rule number 3, I think that all zeros before the non-zero digit are not significant. So the zeros here are not significant. We only have 3 SF. So that is how we multiply, divide accordingly with the scientific notation. Can you follow? You can just go back to this one if this is a little bit fast on you. And later on, I'll be asking you to practice more. Now, next, second to the last lesson is the units of measurement, which is lesson 2.4. So, what are the two systems of unit of measurement? We only have 2 of them. So we have the SI unit, or the International System of Unit, and the English system. The main difference between the 2 of them is the location where we use them, no? And if they use decimals or not, most of them. For the SI unit, or the International System of Unit, it is used globally, and it is a decimal-based measurement. So it's just like what we can see on the table. We have the meters, liters, kilograms, while the English system are mainly used in the US, and it uses the non-decimal units like inches, pounds, and gallons. And the SI units are most commonly used scientifically to express measurements. And I would like you to remember the base SI unit for the 7 major physical quantities that we have. I would like you to memorize them. Okay? All right. Now, aside from the SI units, we use these prefixes to indicate very large numbers. Aside from the scientific notation that we use, which are like this, on the third column, we use prefixes to indicate how we get, or how we read a following measurement. So we can just use this mnemonic, but this mnemonic starts with tera, followed by giga, mega. It looks like parang potato corner order. All right. All right. So we'll start with tera. That's 10 to the 12, or we can say 1 trillion. Giga is 1 billion. Mega is 1 million. Kilo is 1,000. Then hecta is 100. Deca is 10. And we have deci. Starting from deci, it becomes -1. And centi, -2. Milli, -3. Micro, 10 raised to -6. Nano, 10 raised to -1. And pico, 10 raised to negative 12. So we can stop there. Those are the ones that are mostly used. So the mnemonic here tells us the first letters of the prefixes, the metric prefixes. So starting from, just remember these three things. We have King Henry, a milk, chocolate milk, and the time is 9 past. So the first highlighted letters represents the metric prefixes. The is for tera, great is for giga, mighty is for mega, king is for kilo, Henry is for hecto, deca, died is for deca, and the unit here represents that's where we stop before it becomes negative. From drinking chocolate milk until 9 past, all of those are negative. So all you have to do is to memorize the mnemonic and you're good to go and using the prefixes. And this will help us also in getting measurement. But most specifically, the ones that are commonly used here are kilo or 10 raised to 3 and also centi. 10 raised to negative 2 or 0.01. Let's see, how we can use this one later on in our measurements. Now let's just do some dimensional analysis on how we convert one measurement towards another. So the dimensional analysis is used to convert a result from one system to another, or it can be the same system as a unit with a different unit of measurement. So I would like you to remember this general rule in getting or converting a certain unit of measurement. So remember that the given unit is somehow, it looks like it's always on the numerator. It's understood to be over 1. So you have to multiply, you have to put the desired unit always on the numerator. So you can copy that and you can cancel out the given unit below. So this is not always like this. You can have multiples of this. So you can have uh, a conversion factor with which I will be showing you later on. But this is how it should be. So the desired unit should always be on the numerator if that's what you would like to get, right? For example, so let's have this problem. So considering a pin measuring 2.85 centimeters, cm is in centimeters, in length, what is the length in inches? So these are two different units of measurement. Inches is English, centimeters is metric. Now, we have to make use of what we call the conversion factors. Okay, conversion factors. So these are the unit of measurements that are the equivalent of the least number towards the other. For example, we have here centimeters and inches. So our given, you have to write first the given, of course, 2.85 centimeters. And then you can write over 1, but you can also not write that one. But let's just write it for here. And then you have to multiply it onto the desired unit that you have. So you have to put inches here and you have to put centimeters here. Now we have to know how many inches are there in a cm or vice versa. In 1 inch, how many centimeters based from the table? We can say that we have in 1 inch, there's 2.54. So you just have to copy that. So you have here 2.54 on the denominator and then 1 inch on the numerator. So all you have to do is to perform the operation. That's basically 2.85 divided by 2.54. And what's your answer? If your answer is 1.12 inches, then you are correct. So remember, the unit of measurement here will be canceled out. So you can just copy your desired unit of measurement. So that's how we easily convert using a conversion factor. Now you can try this one. Let's say we have 7-inch long pencil and you want to convert it into centimeters. It's the other way around. So write 7-inch multiply, or you can just easily write parentheses over here. So multiply, so your desired unit is in cm and your given unit is in inches. So you can just write this one. So you have 2.54 here and then 1 inch here, cancel out inch. Your answer should be, that's multiplying 2.54 to 7, that's 17.8 centimeters. As easy as that. If the analysis is directly given to us, right? Now, what if we need to have multiple conversion factors? For example, how many seconds are there in 2 weeks? 2 weeks, 2.00 weeks. So you can think of a way to make it direct, but just to show you how, to do the dimensional analysis for this. So for example, so let's write first 2 weeks here. So we can just do it portion by portion. All right. So in a week, how many days? So we have 7 days. So 1 week, always remember that your given unit should be always on the denominator. So 7 days. So we need to get seconds. Now, you can continue in 1 day. How many hours? We have 24 hours. You can continue in 1 hour. How many minutes? That's 60. And then you can still continue. I'll write it down below. In 1 minute, how many seconds? That's 60 seconds. And then proceed with multiplying everything. So cancel out week here, cancel out day, cancel out hour, cancel out minute, and you are left with seconds. What will be the answer? If your answer is very long, you can write it in scientific notation, just like this one. So the final answer is 1.21 times 10 raised to 6 seconds. So that is how we convert dimensionally some simple conversions that we have. Later, I'll be asking you to do more of the practice exercise. But let's proceed with the last portion of this discussion, which is about measurements and sources of errors. So this could be very applicable on your upcoming laboratory experiment. So I'd like you to take note of the following. So here are on the following slides, I'll be showing you some equipment and I'd like you to identify them and what quantity they measure. Have you seen this one before? So this one is called a triple beam balance, which measures mass. How about this one? So this one also measures mass, but we call this the analytical balance. It is enclosed with a glass in between. And we have this very famous, and we will be using this all throughout the semester in our laboratories. We call this a graduated cylinder, which measures the volume of substances, may it be liquid or solid. And we have this one, but without any glass on top of it. We call this one the top loading balance. And it measures mass in grams or in whatever measurement that you have. And mostly a very small amount of substances. We use this. All right, now, what's the difference between mass and weight? So these are mostly used interchangeably sometimes, but in chemistry and physics, they have the difference. For mass, it's a fixed quantity, not dependent on the object's location. So wherever you are, your mass will be the same. But in weight, it has something to do with the pull of gravity of the object, depending on the location. So your mass on the moon is the same on Earth, but your weight on the moon is different from your weight here on Earth because the pull of gravity here on Earth is 9.8 meters per second square, and in moon it's different. And on the other planets also, it's different. So that's how we differentiate mass and weight. And we have these measurements that I have shown you earlier. Okay. And in volume, And so we have this one quantity. Aside from mass, we have this volume. So this tells us the amount of space occupied by an object. So anything that occupies space as volume, basically matter, can be solid and liquid and gases. But for of the volume of regularly shaped solids, we just use the formula length times width times height. For irregularly shaped solid, we use the water displacement method wherein we put uh, the object on the graduated cylinder with a certain amount of liquid, and whatever the water displaced is, that's the amount of volume that we have. Now, in measuring volume, we have this what we call the meniscus. The meniscus is the curved surface in the liquid container because we know that graduated cylinders are mostly glasses. There's is this kind of reflection or a curvature and let's say liquid water. So when we are in the laboratory, I'd like you to measure the volume accordingly. So first is you have to put the graduated cylinder on a flat surface, not holding it, flat surface, and you will see a curvature of water like this. The portion wherein at this is at the lowest is the measurement. So you should be on the eye level. Your measurement should not be here, not there, but below or the below the meniscus, all right? Or the curvature. All right? So that's how we get the volume of the substance using a graduated cylinder. Now with that, talking about mass and volume, two quantities that are related to what we call the density. So the density has something to do with the mass per volume of a substance. So we have the formula with this. So you just have to remember the triangle, right? So this one is a Greek letter rho, right? So rho is equal to m over v or mass over volume. Let's apply this one on a certain problem, and this will also be used on identifying your measurements in the laboratory. You have to think of a way on how to get the density of the objects by using the following materials on your laboratory. Now, in this problem, a small statue has a mass of 78 grams and a volume of 35 cubic centimeters. What is the density? So, in solving problems, you can use the Goresa method later on. So, we have the given, required, equation, solution, and answer. So, now we're given here, we have 78 grams and 35 cubic centimeters. So, you write that as 35 grams and 78 grams and 35 cubic centimeters. So getting the density is just mass over volume. So simply divide and we get the density of the small statue. All right. Which is, the answer here is, let me just, ayan. So we have 2.2 grams per cubic centimeters. All right. Now, so that's just it. Just divide it and we will not be canceling out anything here because we put it on the unit of measurement. We will not cancel anything on that. All right? Okay, now next, how about this one? You can pause the video and try to solve for this one. And you can check your answer on the canvas. And I think I'll be showing it also to you. All right. So you can think of a way on how to solve for this. All right. Now, next quantity is the specific gravity. So this one is dimensionless, meaning it has no unit of measurement. But we use this as a ratio for the density of a solid or a liquid. So we get the specific gravity of the substance by dividing the density of the object and the density of the fluid. So for example, what is the specific gravity of the object with a density of 45 kilograms per cubic meter, knowing that the fluid that we will be using is just water, for example, the density of water is 1,000, right? So 45 divided by that. So it's 0.045. All right. So that's how we get the specific gravity of the object. And of course, we have temperature as a unit of measurement. So, quantity rather. For temperature, we use Kelvin as the main as a unit of measurement. But I would like you to remember this for units of measurements that we have for temperature, or the formula for temperature, because this will be necessary. All you have to do is to remember if we are getting Fahrenheit and then we have Celsius. Okay, you can take a screenshot of this and we'll apply it right away on our next problem. So for example, we have a solder, which is an alloy, as a certain melting point of 224 degrees Celsius. What is its melting point in degrees Fahrenheit? So following the Bresa method, we have the given 224. We have the required to get is the degree Celsius from Fahrenheit. So we'll be using the formula number 1. All right. So you just have to put it directly on your calculator. And we will be getting 224 degrees Celsius, 9 over 5 plus 32. That is equal to 435 degrees Celsius. So you just have to follow the formula as is, nothing more, nothing less, and you'll get the answer. All right. So you can try the next problems here. You can take a screenshot, pause, and then check on your answers later on. And lastly, for the types of errors, we have 3 of them. So we have the systematic error, which are composed of can be personal error, your error, and method error is something to do with the instructions that you're following in the laboratory. And it could be a device error or measuring device error. So these are the errors that can be found when we are doing experiments, by the way. We have the systematic error, we have the random error, and the gross error. For the random error, it has something to do with the specific problem in the measuring apparatus that we have that affects the precision of the measurements. And for the gross error, these are the most obvious error that is shown in a certain experiment. So for us to be able to understand more of this, let's try to apply it. So identify the type of the error based on the given scenario that we have. So we have a digital scale in the laboratory, which reads always 5 grams more than the actual mass. So this is a calibration error, and we can consider this as a systematic error. Next, a student reads the mercury level slightly above or below the meniscus each time due to inconsistent eye position. We can consider this as a random error, all right? Because it has something to do with how we use the laboratory apparatus. All right. Next, we have a student presses the stopwatch 1 to 2 seconds late due to distraction during a school sport event. So this is a very obvious error. So we can consider this one as a gross error. And the student measures 50 milliliters of water using a beaker, which is not precise for volume measurement. We call this a systematic error because in the first place, you use a wrong measuring device instead of using the right device to measure it. All right, so how do we minimize the error? We just follow the following steps. So we have to calibrate it correctly. So meaning we have to start at 0 if needed and repeat the measurements. So at least 3 trials minimum. And of course, in the laboratory, you have to be careful, you have to be focused, and always double check your work. Always work in pairs, right? All right, so here's the chapter wrap up, and I'd like you to answer this maybe some other time, no, when we see each other again. And For your practice exercise, answer the following practice exercise, and we'll try to answer this before your quiz on Friday as a review for and to check if you really tried to watch the lecture video discussion.